The free energy paradox states a simple but unsettling truth. Physics never explicitly forbids devices that output more usable energy than they consume. Yet every attempt to build one has failed with absolute consistency. The laws appear permissive, but reality behaves as if a hidden clause blocks the very idea from taking shape. This gap between what the equations allow and what the universe enforces creates a tension that feels almost sentient in its refusal to yield. Classical mechanics offers no line that reads, "Perpetual energy is impossible." Thermodynamics forbids perpetual motion, but only under specific assumptions about disorder, temperature, and equilibrium. Quantum fields fluctuate endlessly, space itself seethes with vacuum energy, and mass energy equivalence implies unimaginable reservoirs embedded in ordinary matter. Theoretical abundance surrounds us, yet every practical design collapses into loss, friction, or entropy the moment it touches the physical world. It's as though the universe shows you infinite energy at arm's length and then retracts it the instant you reach. Look closely at the vacuum. Quantum mechanics predicts constant creation and annihilation of particle pairs, momentary bursts of energy permitted by uncertainty. Nothing stops us from imagining a mechanism to siphon these fluctuations. Yet the instant we try to interact with them, the system stabilizes and the excess vanishes, as if observation itself seals the vault. You are allowed to see the turbulence but never redirect it. What this reveals is not a failure of engineering but a deep structural irony. The laws of nature present energy as fundamentally abundant while simultaneously enforcing pathways that make its extraction unavoidably costly. Unlimited energy feels mathematically plausible yet operationally forbidden, a permission that behaves like a prohibition. And in that contradiction lies a portrait of a universe that invites understanding while guarding its most tempting source of power. The paradox sharpens the moment you examine the mechanism itself. If energy in the universe is conserved, then nothing in principle prevents a clever system from tapping into the vast reservoirs woven into matter, motion, or the vacuum. Physics does not restrict the amount of energy that exists. It restricts the pathways through which energy can be transformed. The tension emerges when every conceivable pathway to free energy collapses into the same constraint. The act of extraction destroys the very conditions that make the reservoir appear usable. What looked like abundance turns out to be structure disguised as freedom. Start with the simplest case, a device that claims to output more work than it takes in. Mechanics offers no direct prohibition, only the requirement that forces and motions balance. But the moment the device begins to operate, friction, thermal leakage, and electromagnetic losses convert organized energy into disorder. No component escapes this cascade. Each attempt to close the loop amplifies entropy faster than it amplifies usable work, revealing that the mechanism fails not because it violates the equations, but because it must obey all of them at once. The system loses coherence just as it promises to become self-sustaining. Move deeper into quantum systems. Zero-point fluctuations look like an endless ocean of energy rippling beneath reality. Equations permit them, the vacuum demands them, yet any instrument designed to harvest them dampens the fluctuations it tries to exploit. Interaction forces the vacuum into a lower variance state, erasing the very instability that suggested free energy in the first place. You don't drain the vacuum, you stabilize it. The pattern becomes unmistakable. Every mechanism that seems to unlock unlimited energy works only as long as it remains imaginary. The instant it becomes physical, the universe adjusts, sealing the opening that reason momentarily revealed. The free energy paradox deepens when we confront a principle that sits quietly beneath every physical process. Order is never free. Any device that claims to generate more usable energy than it consumes must also generate a surplus of order, a structured, directed flow that can perform work. But nature treats order as a kind of currency, one that must always be paid for, even when energy itself appears abundant. What looks like a loophole in thermodynamics becomes a debt written into the architecture of reality. Consider how work actually arises. A system doesn't produce work merely by having energy, it produces work by having organized energy. Gradients, differences, asymmetries. Heat does nothing until there is a temperature contrast. Charge remains idle until a potential forms. Motion carries no usefulness until it becomes directionally constrained. Every mechanism that harnesses energy depends on these gradients, and every gradient collapses the moment you try to extract more than you put in. The device doesn't run out of energy, it runs out of structure. This is why perpetual machines fail in the same predictable way. Their internal organization slowly erodes as microscopic disorder accumulates. Bearings misalign, fields blur, oscillations lose coherence. Even in perfectly sealed systems, statistical noise pushes the device toward equilibrium where no gradient remains to exploit. The universe doesn't intervene dramatically. It simply lets disorder win by default, quietly and inevitably. Quantum systems obey the same logic at a deeper level. You can momentarily amplify fluctuations or capture fleeting energy spikes, but doing so requires measurement or confinement. Both actions impose order, and the cost of imposing that order always exceeds the energy you hope to extract. You don't lose energy, you lose the asymmetry that made it accessible. The paradox tightens here. Unlimited energy seems possible because energy itself is plentiful, yet every attempt to access it encounters the universal scarcity of order, a resource more fragile than energy and far more decisive. The free energy paradox becomes even sharper when we confront how often physics gestures toward infinite or near infinite reservoirs. Space is filled with vacuum energy. Atomic nuclei trap colossal binding energies. Gravitational fields extend forever. On paper, these sources look like open doors, vast wells we should be able to tap with nothing more than precision and ingenuity. The equations describe a universe saturated with potential, yet our technology interacts with it as if all that abundance were sealed behind unbreakable glass. The result is an illusion of accessibility that dissolves the moment we try to touch it. Vacuum energy is the clearest example. Quantum field theory assigns a non-zero energy to empty space, a value so enormous that a single cubic centimeter of vacuum could, in theory, dwarf the output of all human power plants combined. Nothing in the formalism says this energy cannot interact with machinery, but when we attempt to couple a device to the vacuum, the interaction necessarily redefines the boundary conditions of the field. Instead of letting energy flow outward, the system adjusts its ground state to remain stable. The infinite supply becomes inert, the instant extraction becomes possible. Infinity exists, but only as a background condition, never as a fuel line. Nuclear energy offers the same mirage on a different scale. The binding energy trapped in matter seems almost limitless compared to chemical fuels. Yet accessing it requires extraordinary confinement, catalysts, or instabilities. The more extreme the reservoir, the more extreme the conditions required to unlock it. And those conditions consume energy faster than the reservoir can release it. We can approach the boundary, but never cross it without paying more than we gain. Here, the paradox clarifies itself. Physics displays endless energy, not as a resource, but as a horizon. Always visible, always expanding, and always receding the moment we try to arrive. The paradox acquires its sharpest edge when we recognize a universal pattern. The moment you try to extract energy from a system, you change the system itself. What looked stable becomes perturbed, what looked abundant becomes diluted, and what looked accessible becomes self-protecting. This isn't a philosophical observation, but a physical rule embedded across every scale of nature. The act of harvesting energy alters the reservoir in ways that erase the very advantage you hope to exploit, as if extraction and disruption were two sides of the same equation. Consider magnetic fields. A region of strong magnetic flux seems like a ready-made energy gradient until you place a coil inside it. The coil's induced current generates its own magnetic field, opposing the original one. The stronger your attempt to extract energy, the more you cancel the source. You don't drain the field, you reshape it into a weaker version of itself. Gravitational systems behave with the same symmetry. A spinning planet holds staggering kinetic energy, but any machine designed to siphon that rotation, tides, torque transfer devices, orbital tethers, inevitably slows the planet down. The reservoir shrinks in direct proportion to the extraction. You cannot take energy without rewriting the very motion that stored it. Even biological metabolism follows this rule. Cells extract energy from chemical gradients, but the extraction reduces the gradient, forcing the organism to continually rebuild the difference it depends on. Every gain diminishes the source and demands its reconstruction. At the quantum scale, measurement itself becomes a form of extraction. Observing a fluctuation collapses possibilities, stabilizing what was once dynamic. The system loses the very instability that seemed like a source of extra energy. This pattern reveals a deeper truth. Energy is never simply there. It exists as a relationship, one that collapses the instant we try to exploit it. The universe gives us reservoirs that shrink precisely when touched, turning abundance into evanescence by the act of reaching. The free energy paradox turns more intricate once we examine why systems resist giving up their stored energy so easily. Stability is never accidental. It is the product of countless microscopic balances that hold a system in a particular configuration. To extract energy, you must disturb those balances, and the disturbance itself imposes a cost. What feels like an obstacle is actually a byproduct of stability. The more stable a system is, the more energy you must invest to move it away from equilibrium. Energy is locked not by scarcity, but by the precision with which stability maintains itself. Take atomic nuclei. Their binding energy is immense, but that immensity is a sign of how strongly the particles are locked together. The nucleus is stable because releasing its energy requires pushing it into an unstable configuration, which demands immense external input. The energy seems abundant only when viewed from the outside. From the inside, it exists as tension perfectly balanced, resistant to interruption. Chemical bonds follow the same logic. A molecule's stored energy is simply the result of electrons arranging themselves into the lowest energy configuration available. To unlock that energy, you must force the electrons into a higher energy state first, a cost paid up front before any gain can be collected. The release is dramatic only because the preparation was expensive. Even gravitational systems illustrate this hidden price. A massive object in a deep gravitational well theoretically has vast potential energy relative to infinity. But extracting that energy requires lifting the object out of the well, fighting the stability that the geometry of space-time itself enforces. The energy is real, but it lies on the far side of the effort required to reach it. The insight crystallizes. Systems don't hide their energy. They spend it maintaining the order that defines them. The stability we take for granted is the barrier that makes unlimited extraction fundamentally elusive. The paradox tightens when we confront the silent rule that governs every exchange in nature. You cannot extract energy without increasing uncertainty somewhere else. This isn't merely the second law of thermodynamics in disguise. It is a deeper principle linking information, entropy, and physical change. Whenever a system yields organized energy, some part of the universe must absorb the cost of lost predictability. The accounting is perfect even when the process appears clean. What looks like a loophole becomes a bookkeeping law written into the fabric of information itself. Start with thermodynamics. When a machine produces useful work, it channels energy through a controlled gradient. But maintaining that control requires precise states: direction, timing, structure. As the machine operates, microscopic details blur. Vibrations spread, temperatures equalize, surfaces roughen. The loss of fine-grained information shows up as entropy. You gained work, but you lost certainty. The system pays for your order by increasing its disorder elsewhere. Information theory sharpens this insight. Erasing or compressing information, actions essential for any functional device, requires converting structure into noise. Landauer's principle quantifies the cost. Every bit of information destroyed releases heat. Even logic, at its most abstract, cannot operate without paying an energetic fee. Trying to make a device more efficient simply shifts where that cost appears. It never removes it. Quantum mechanics completes the trilogy. Extracting energy from a quantum state reduces its range of possible outcomes. But to do that, you must gather information about the system, and gathering information forces the system to randomize something else. Precision in one place demands uncertainty in another. The universe enforces a perfect symmetry between knowledge gained and instability generated. Here the paradox reveals its spine. Unlimited energy fails not because energy is scarce, but because certainty is. The universe allows boundless power in theory, while making the cost of accessing it proportional to the order you disturb in the process. The free energy paradox becomes even more revealing when we push efficiency toward its theoretical maximum. As a device becomes more efficient, it wastes less energy and produces more usable work from the same input. Yet there is a boundary it can approach but never cross. That boundary is not mechanical or technological, it is geometric. The space of all possible states narrows as efficiency climbs, forcing the system into ever more fragile configurations. High efficiency is simply another form of order, and extreme order is exquisitely difficult to maintain. The closer a machine gets to perfection, the more the universe amplifies the smallest imperfection. Consider a heat engine. The Carnot limit defines the maximum efficiency achievable between two temperatures. Nothing in the math forbids reaching it, yet doing so would require infinite time, perfect insulation, and fluctuations approaching zero. As you raise efficiency, the allowed pathways for energy flow shrink until any deviation, thermal jitter, or microscopic chaos shatters the ideal. Approaching perfection makes the system more sensitive, not more powerful. The pursuit of limitless energy becomes indistinguishable from the pursuit of infinite precision. Electrical systems reveal the same fragility. A perfectly lossless conductor would carry current indefinitely, but maintaining such a state demands absolute exclusion of disturbances. Superconductors demonstrate how close we can get, yet only under extreme cold, isolation, and purity. Raise the temperature by a fraction, introduce a defect, or allow a stray magnetic field, and the resistance reappears instantly. Perfection collapses under the weight of its own requirements. Even biological systems illustrate this diminishing return. Metabolism becomes more efficient by refining molecular pathways, but each refinement introduces new vulnerabilities. A hyper-optimized organism is powerful only in a narrow band of conditions. Outside it, the system fails abruptly. Here the paradox sharpens into focus. The closer we move toward perfect efficiency, the more the universe demands impossible stability. Unlimited energy doesn't fail because perfection is forbidden. It fails because perfection cannot survive contact with reality. The free energy paradox reaches its most counterintuitive form when we examine the relationship between control and power. To extract energy, a system must impose constraints, directing motion, shaping fields, maintaining gradients, suppressing noise. But each layer of control requires its own energy, its own feedback loops, its own structural delicacy. The more tightly you try to control a system, the more energy you must spend to keep that control intact. And past a certain threshold, the cost of maintaining control exceeds the energy that control was meant to harvest. Power demands control, yet control consumes power. Imagine a machine designed to capture tiny fluctuations, thermal noise, molecular jitter, or quantum fluctuations. To do this efficiently, it must amplify the faintest signals while rejecting the surrounding chaos. But amplifiers generate heat, filters leak entropy, and every stabilizing mechanism adds its own turbulence. As the apparatus becomes more precise, it becomes more unstable because precision magnifies the consequences of even the smallest disturbance. Control sharpens the signal while sharpening its own vulnerabilities. Macroscopic systems follow the same logic. A highly optimized turbine demands exact blade geometry, flawless lubrication, and perfectly balanced loads. The tighter these constraints become, the more energy and engineering effort is required to enforce them. A tiny deformation, a micro impurity, or a transient temperature shift unravels the gain. The system works best when the world behaves perfectly, but the cost of enforcing perfection rises faster than the energy extracted from it. Even cognitive systems mirror this pattern. The brain can focus intensely, extracting remarkable insight from minimal data, but sustained precision drains metabolic resources disproportionately. Concentration narrows possibilities while consuming the energy that grants it. This reveals a profound symmetry. Control is not free, and the cost of ultimate control is ultimate expenditure. Unlimited energy fails not because nature withholds power, but because the act of harnessing power demands a level of control whose price grows without bound. The free energy paradox reaches its structural core when we examine closed loops, systems designed to feed their own output back into their input. At first glance, a closed loop seems like the perfect architecture for unlimited energy. Once the device is running, it should sustain itself, amplifying its own power with each cycle. But every closed loop in physics encounters the same fate. The loop does not amplify itself. It exposes every hidden loss, every microscopic imperfection, every leakage of order into entropy. A closed loop is not a path to infinity. It is a magnifying glass for weakness. Consider an electrical oscillator. In theory, a resonant circuit can circulate energy indefinitely. Yet the moment you build one, resistance, radiation, and quantum noise slowly drain the oscillation. To compensate, you add amplifiers. But the amplifiers introduce their own noise and their own heat, which must be removed by additional subsystems. Each layer added to perfect, the loop increases the conditions it must satisfy. The loop becomes more exacting, and thus more fragile. Mechanical loops behave no differently. A rotating flywheel loses energy through air drag, bearing friction and material deformation. Attempts to reduce these losses, sealing the chamber, using magnetic bearings, refining the mass distribution, reduce dissipation, but amplify sensitivity. The more perfectly the wheel spins, the more catastrophic the consequences of the slightest imbalance. A single microcrack ends the entire cycle. Even thermodynamic engines hit the same wall. A perfectly closed thermal loop would require heat to flow from cold to hot without cost, an inversion of every statistical rule governing matter. The loop doesn't just fail, it reveals why failure is guaranteed. This is the final shape of the paradox. Any loop designed to create infinite energy ends up amplifying entropy instead. The very architecture meant to liberate energy becomes the stage on which the universe demonstrates its refusal to allow perfection to sustain itself. The free energy paradox stops being a puzzle of machines once we look past the engineering details and see the deeper structure tying all these failures together. Every mechanism collapses not because it violates a specific rule, but because it attempts to bypass a principle that hides beneath all physical laws. The universe preserves consistency by restricting how differences can be created, maintained, and exploited. Energy is plentiful, but usable differences, gradients, asymmetries, instabilities, are inherently finite. The universe allows boundless energy, yet limits the leverage points through which it can flow. What seems like a technical barrier is actually a structural safeguard. At each scale, this safeguard takes a different form. In mechanics, attempts to sustain motion meet friction and deformation, not arbitrary obstacles, but the natural consequence of atoms interacting. In thermodynamics, extracting work consumes order and elevates entropy. Not a punishment, but the statistical result of redistributing microstates. In quantum systems, measurement collapses fluctuation. Not a trick, but a reflection of how information and reality intertwine. These are not separate limitations, they are multiple expressions of one principle. The universe resists the creation of perpetual asymmetry. Seen from this higher angle, free energy fails because it seeks to capture a gradient without paying the cost of maintaining it. It imagines flow without sacrifice, direction without dissipation, organization without degradation. But gradients exist only when the universe tolerates imbalance, and every interaction pushes the system back toward equilibrium. The more extreme the imbalance you try to exploit, vacuum fluctuations, nuclear forces, superconductive states, the more violently the universe restores symmetry. The closer you approach infinite energy, the smaller the corridor in which your device must operate until perfection becomes indistinguishable from impossibility. This reveals the paradox in its pure form. Physics does not forbid unlimited energy, it forbids unlimited asymmetry. Unlimited power is conceptually allowed but dynamically unreachable because the pathways that deliver power cannot remain perfect. The laws do not ban free energy, they simply tie it to structures that collapse under their own precision. And here the contradiction becomes coherent. The universe is not teasing us with abundance, it is protecting the integrity of its own equilibrium. The impossibility of free energy is not a failure of physics, it is physics working flawlessly. The free energy paradox resolves itself once we stop imagining energy as a substance waiting to be claimed and recognize it instead as a pattern that must be sustained. Energy becomes usable only when differences exist, and differences survive only when the universe allows them to. What defeats free energy is not the scarcity of power, but the fragility of the asymmetries required to channel it. The moment you attempt to extract infinite work, you demand infinite stability. And stability is the one currency the universe refuses to provide without limit. Every failure, from mechanical overreach to quantum collapse, points to the same realization. A perfectly self-sustaining system would need to outrun entropy, noise, fluctuation, and statistical drift. It would need to impose direction in a universe that constantly dissolves direction back into equilibrium. Unlimited energy is imaginable only if nothing ever perturbs the system, if no interaction ever leaks information, if no microscopic uncertainty ever accumulates. In other words, it requires a universe that is not this one. Yet the paradox is not bleak, it is clarifying. The impossibility of free energy is the reason stars burn predictably, atoms remain bound, and life can build complexity without collapsing under runaway forces. What looks like restriction is actually the quiet architecture that makes stability, structure, and consciousness possible. Unlimited energy doesn't exist because the universe prioritizes coherence over excess, and so the paradox ends where it began. Physics permits infinite energy in theory, but protects reality by limiting the structures that could access it. Infinity stays in the equations. Finitude shapes the world you inhabit. If you understood the paradox, write in the comments, I see why infinity stays untouchable.